Dear students, welcome to the Department of Electronics first unit class. This is your class. So first let us revise what we studied in the last class. What we studied? We studied the basic discrete time signals, step function, impulse function, ramp function, exponential function and the sine function. What we studied? We studied all these types of the basic discrete, all these types for the basic discrete time signal. Why I am again explaining this means the same signals we studied for the basic continuous signals also. Okay, please be careful in the examination. Okay, first read the question carefully. Depends on that, write the answers. If we asked for the continuous time signal, then you have to explain the all these signals with respect to the continuous signals. If we asked for the discrete, then with respect to discrete time signals, you have to explain. In today's class, we are continuing the exponentially damped sinusoidal signals and the pulse signals for the discrete time signals. Okay, and once again the same thing, the same signals you studied for the continuous also, but in this class we are continuing with the exponentially damped sinusoidal signals and the pulse signals for the discrete time signal. And also we are going to complete the properties of the systems. Okay, nearly I think 7 properties are there: linearity, causality, stability. Like that, some properties are there for the systems that also we are going to complete in this session. Okay, first begin the session with the exponentially damped sinusoidal signals. Okay, so how we are going to define this exponentially damped sinusoidal signals means the discrete time version of the exponentially damped sinusoidal signal is described by this x of n is equal to b r to the power of n sine omega n plus phi. Only this is the definition of the exponentially damped sinusoidal signals for the discrete time versions. Next, we are going to write that for the signal to decay exponentially with time, the parameter R must lie in the range in between 0 and 1. Only if you remember this means it is sufficient. Next, we will go for the pulse signals. In the continuous also, we studied the pulse signals. That continuous time signals also, we are having the two types of the pulse signals. One is the rectangular, another one is the triangle. Here also the same thing. One is the rectangular pulse signal and another one is the triangular pulse signal. Rectangular pulse signal is defined by n by 2 n is equal to 1, where your modulus of n is less than or equal to n. Otherwise its value is equal to 0. This is the graphical representation of the pulse signal for the rectangular pulse. Okay, here this is the n, and here this n value is lies between minus n and the plus n. This that is rectangular n by 2n. This x-axis represents this rect of n by 2n. Its value is equal to 1 in between the minus and the plus 1. So that is why all the values are at the 1. For other values it is equal to 0. This is the definition for the discrete version of the rectangular pulse. And this is the graphical representation of the rectangular pulse signal. Next, let us move to the triangular pulse signal. So this is defined as triangular of n by n is equal to 1 minus modulus of n by n, where modulus of n is less than or equal to n. Otherwise, its value is equal to 0. So actually, this is the graphical representation of the triangular pulse signal. Okay, here what is that means? This is equal to this one means its value is decreasing from this end to this end and from this end to this end, but this triangle value is or lies between the plus n to the minus n. The signal x of n is equal to tri of n has 2n plus 1 samples over minus n to plus n, with the terminal samples of x of n and x of minus n being 0. Terminal points is 0. That you should remember. Terminal points is nothing but what? End points. Okay, this end points. You see x of n is also equal to 0 and x of minus n is also equal to 0. Okay, this is about the discrete time signals, pulse signal and the exponential signals. Okay, remember that students in the examination they may ask one or two signals or they may ask the full signals for the 6 marks questions. Okay, now we will move to the properties of the system. In that, first one is called the linearity. Okay, let us see the definition of the linearity. What is the definition of the linearity? The discrete time system described by T, it is called overall operator. T overall operator is linear. Okay, if this is a one, you think that this is a one signal, and it is which type of the signal? Discrete time signal. This is called linear. When we are going to call it as a linear, if the response to a weighted sum of inputs x1 of n and x2 of n is weighted sum of the response of the two inputs separately for all weights and all acceptable signals x1 of n and x2 of n. Okay, what is the linearity means? So I will tell you one simple example for this one. Okay, here I am having the two signals. I will take the signal 1 as x1 and x2. Okay, x1 I am going to multiply it by 2. x2 I am going to multiply it by 4. What is linearity means? Let us take y is equal to linearity. So separately they have to multiply, that is 2 of x1, different weights here. This is called the weights. Okay, so final output I am going to write it as 2x1 plus 4x2. That is nothing but what? The linearity. We will see once again the definition here. If the response to a weighted sum of inputs x1 of n and x2 of n, here x1 of n and x2 of n are the two weighted inputs, and its weighted sum of the response to the two inputs separately for all weights and all acceptable signals x1 of n and x2 of n. Okay, we will see the expression here. Here you see what they are taking means the system described by T of linear is linear if the following relation is observed. What is the relation means? This is the relation. Okay, what is the relation? T of, here you see here, this is the relation a1 x1 of n plus a2 x2 of n. Here a1 and a2 are the weights. Okay, how I have taken here 2 and the 4, no, like that commonly generally we are writing, so we have taken as a1 and a2, and this can be written as how we are going to write if it for satisfying the linear property means You should write A1 separately, T of x1 of n plus A2 T of x2 of t. That means that T is multiplied separately to these two inputs. Then it is called a linearity. In precise, a system is linear if it obeys the principle of superposition. And another one thing is for the precision values, another one thing is the linear means it obeys the principle of superposition theorem that you studied in the first semester. A similar definition is holds good for the continuous time signal also. This is the uh, definition for the discrete time signal, and continuous means what you should do, just you change instead of n, if you are changing for t, then it is the similar definition for the continuous time signal. Let us hope all of you understood this linearity, that is a one property. The another property next, that is causality. It is also the same thing what we are usually saying casual. Okay, you see the definition, you can compare that. What is the causality means? A system is said to be causal if the present value of the output signal depends only on the present value or past value, or a combination of present and past value of the input signal. Okay, what is the definition of the causality means is nothing but what, if we are giving the input to the any system, then we are going to get the output. Okay, that is a one causal system for the any system. A system is said to be causal. Okay, if the present value of the output signal, present value depends on the output value maybe depends on the present value or the past value or the combination of present and past values of the input signal, then that system is called causality system. Okay, and here one point I will tell you, please note down the definition of the system. In the examination they may ask what is system for 2 marks. Okay, please be careful or be note this point. Okay, note down the definition of the system here. And let us see the next. A discrete time system is causal if the output at n is equal to n naught depends only on the input for n is less than or equal to n naught. This is the one condition. Okay, when the discrete time system is going to, when we are going to say that the discrete time system is causal if the output of n is equal to n naught depends only on the input for n is less than n naught. Similarly, a continuous time is defined the causal. Continuous time, when we are going to say that the continuous time to be causal, if the output at t is equal to t naught depends only on the input for t is less than or equal to t naught. For example, an input-output relation of the form y of n is equal to x of n plus x of n minus 1 belongs to a causal system. Okay, this is a one expression. This type of the expression belongs to the causal system. So next is the third one is time invariance. Okay, what is the time invariance is, if you are delaying in giving the input, the same time will take to get the output. Okay, for example, if after switch on the system, if I am giving the input after 5 nanoseconds, the output also you are going to get after 5 nanoseconds. That is called what, the time invariance property. Let us see the definition of that one. A system is said to be time invariant if a time delay or time advances of the input signal leads to an identical time shift in the output signal. Okay, the same identical time shift. It may be the time advance or the time delay. Both are going to accepted here. The same thing is going to identical time shift in the output signal. Okay, let us see here. For example, the discrete time system T of this is a time invariant if this signal is time invariant if all x of n and n naught we have t x of n minus n naught is equal to y of n minus n naught. That means input you are giving by n minus n naught, in the same way you are going to get the output is at also n minus n naught, where y of n is equal to t x of n. What is your y of n? Y of n is equal to t x of n. The same thing if we applied for the continuous time signal, then what happens? X of t at t naught. This is x of n and n naught is your discrete time system, whereas x of t at t naught is your continuous time signal. The same thing is that t x of t minus t naught is equal to y of t minus t naught, where what is y of t? Y of t is equal to t into x of t. Okay, now we will move to the next property, that is called the memory. Okay, so it is a one common name. What is memory? Okay, what is memory? So if you want to store anything in your system, then it needs a memory. Okay, so here let us see in detail about this memory, what it is in the DSP. Okay, a system is said to possess the memory. A system is said to possess memory if its output signal depends only on the past value of the input signal. Okay, when we are going to say that a system has the memory, that means its output signal depends on only the past value of the input signal. Okay, for example, also you can say that in the system or in the laptop or in the mobile, what we are doing, we are saving something. Okay, and whenever you are seeing, that is a past value. Just you think that you have taken the photo before 1 year, now you are seeing that is the past value. That is nothing but what a system is possess the memory. That means it has the memory. Okay, on the other hand, another definition is also there. A system is said to memoryless. What do you mean by the memoryless? That means if its output signal depends only on the present value of the input signal. Okay, only for the present value. If you are present value of the input signal, if you are getting the output, then it is called the memoryless. Can you give any one simple example for the memoryless? Just one common example means, okay, in the first year and in the second year you have done the some practicals. Okay, that practical you are giving the input and it is going to give you the output. We can't save that or we can't store that data. Okay, so that is nothing but what we can just I am explaining you or I am just giving the example. Okay, that also we can call it as memoryless. But one electronics device is also there. A resistor is called the memoryless because it is not saving any, it is not storing any data. Okay, since IFT through it may be anytime t depends on the voltage across at the same time t, that is IFT is equal to V of t divided by R. Okay, on the other hand, okay, I of t is equal to V of t divided by R. This is for the resistor. Resistor is called the memoryless device, whereas inductor is a memory device. Okay, we are saying that it has the memory. The current I of t is given by 1 by L is equal to minus infinity to t, where V of tau into d tau. The current at t is equal to 0, that present value depends on voltage for t is less than equal to 0. That is for the past value it depends. So that is why we are going to call it as a inductor has the property of the memory, whereas resistor is called the memoryless device. Okay, this is all about the memory. Now we will move to the another one, that is for a similar concept is true for the discrete time system also. An example for the input output relations belongs to the system having the memories y of n is equal to x of n plus x of n minus n. Now we will move to the another one, that is stability. Actually, what is the stability? The stability means a discrete time system is bounded input bounded out, that is bounded input and bounded output stable. If every bounded input signals produces a bounded output sequence, that means one the simple and the common definition is nothing but what? It has a one boundary for the input, and in the same boundary it is going to produce the output. That is nothing but what? The bounded input, bounded output stable. Okay, and here that is the, once again we will see the definition. A discrete time system is bounded input, bounded output stable. When we are going to call it as a bounded input and bounded output, that is BIBO stable, if every bounded input sequence produces a bounded output sequence. Okay, if we are giving the bounded input to the system, means it should produce the bounded output. Okay, that means it has some limitations. Okay, in that limitation only we are giving the input, and the same limitation it should produce the output. So that is why it is called a bounded input, bounded output stable. Okay, mathematically if we are writing means, how we are writing means the modulus of x of n, that means it is a signal. X of n is nothing but what? Your discrete time signal is less than or equal to m of x is less than or equal to infinity. Then for bounded input, bounded output stability, the output y of n must obey the condition that y of n is also less than or equal to my less than or equal to infinity. Correct? If input is obeys this condition, means the output should also obeys this condition. Okay, that type of the system are called at the stability. A similar definition holds good for continuous time system also. An example is, let us investigate BIBO stability of the discrete time system whose input-output relation is given by. In the next slide, I will show one small derivation is there for this one. Okay. So, for example, what we are doing, investigating BIBO stability of a discrete time whose input-output relation is given by this one. Y of 3 is equal to 1 by 3. Sorry. X of n plus x of n minus 1 plus x of n minus 2. Let x of n is equal to modulus of less than or equal to mx less than or infinity. This is what your bounded input. Okay, this is your y of n. So we are taking this one. Then y of n is equal to 1 by 3 x of n plus x of n minus 1 plus x of n minus 2. This implies y of n is less than or equal to 1 by 3 modulus of x of n plus modulus of x of n minus 1 plus modulus of x of n minus 2. By translating a sequence, the bound on the translated sequence does not change. Thus, y of n mod of y of n less than or equal to 1 by 3 mx plus mx plus mx. So it implies that this output signal is less than or equal to mx is less than or equal to less than infinity. This is called the bounded output. Hence, we are going to say that the system is under investigation is bounded input and bounded output stable. Okay, go through it again. Just it is a simple mathematics is there. Now, we are having the final property of a system is invertibility. What do you mean by the invertibility? Means a system is said to be invertible if the input to the system may be uniquely determined from the output. A system is said to be invertible if the input to the system may be uniquely determined from the output. In order for a system to be invertible, if we want to say that a system is invertible, means it is necessary for distinct inputs to produce the distinct outputs. Okay, what is its? So I will continue complete this one. In other words, given the two inputs x1 of n and x2 of n, with x1 of n and x2 of n are not equal, and it must produce the outputs are also not equal. Okay, what is invertibility? So how you are going to remember that means, invert means what? Reverse. Okay, so in the DSP, what happens? What is the invertibility? When we are going to say that a system is invertible means, you think that we are applying a different inputs to produce the different outputs. Okay, in some systems we need this type of the outputs. Okay, that is called actually the invertibility. Okay, in some system, or we, if we want to check that the system is invertible or not, what should be the condition? We are applying two distinct inputs, that means two different inputs I am applying. So what they have taken here, they told that in the next sentence you see x1 of n and x2 of n are the two inputs and they are not equal. If inputs are not equal means definitely they are not going to produce the outputs are same. So they are going to produce the different outputs. So this is the one condition. If these two are not equal, in the same way what happens, y of n and not equal to y2 of n, this is output. Y of n is the output for the input x of n, x1 of n, y2 of n is the output for the input x2 of n. Okay, if inputs are different, outputs is also different for the same system, then that is actually that is a one property of the then invertibility. Then we are going to call that the system has a invertibility property. Invertible. The same definition holds good for continuous time also. Here we have this we have explained for the discrete. How we are going to say that it is discrete? Here we have taken the inputs as n. Okay, if you want to apply for the continuous time signal, what you are going to do, x1 of t is not equal to x2 of t. It must be true for y1 of t is not equal to y2 of t. Okay, so these are the reference books. Dear students, please be carefully watch the video, make the notes. Okay, okay, you have to carefully watch the video. If possible, try to watch the video thrice or fourth time also for better understanding. Okay, and this is what my concern about my students. Okay, meet in the next video.